Hello. Today we will talk about radiometry and rendering equation. These are the class objectives. I wish at the end of this lecture you can understand hemispherical coordinate and integration method. So we will talk about various radiometric quantity. One of the most important radiometric quantity is the radiance. And we will talk about Bayesian material functions like BRDF. And again, at the end of this lecture material, we will talk about render equation, which is extended version of the radius equation that we talked about last time. Let me briefly talk about why we need this radiometric quantity. In the end, in this scene, once we get the geometry of this scene or some material information about this scene, in the end, we want to know what are actually the light energy that we can see from from our eye position to that direction, right? So in other words, in the context of ray tracing, once we generate ray from here to there, we want to know how much energy, in other words, how much color we can see from here to that direction. To answer that the question, in the end, we need to know how much energy we can see from that point to that direction. Once we know that energy, then based on that energy, we can compute the color, the level of the illumination, and that's in the end, that's the radiance. Before we talked about the details about our today lecture material, in the end, there are four major factors for the light and material interactions. In the end, we need to consider these light and material interactions for computing that energy for each ray. First, we will talk about physics of light, and then we will move on to the radiometry. Then also we will talk about material property. In the end, we will end this lecture material by talking about rendering equation. There are different types of the models of light. The detailed model is quantum optics. It's one of the fundamental models of light. It explains well the dual wave and particle nature of the light. But just to generate images, to generate the image, considering this quantum optics takes too much time. And so instead of that, when we need to consider the wave property of the light, we typically use the wave model of the light. It is simplified quantum optics. It explains these wave features like diffraction, interference, also the polarizations. I don't think that we are using the CD anymore. But if you had a chance of to look at the backside of the CD, you can see that this kind of the color pattern, right? That's the feature of the wave. That's the feature of the wave property of the light. This is actually known as this diffraction. There are very small small details on the backside of the CD, and then the size of that feature actually very small, and then that even very close to the wavelength of light. So because the size of the object is very similar to the wavelength of light, we can see this wave feature. So actually there are some sort of this diffraction. Also, at some cases we can also use this wave model to simulate this kind of wave feature. But in most of cases, for generating images, we typically use the geometric optics, which is most commonly used one in the computer graphics. In this model, we assume the size of objects much bigger than wavelengths of light, so that we don't see the wave feature. Instead of a lot of cases, only the particle property of the light actually a dominant one. So at that cases, light is emitted, reflected, also transmitted like this particle. Also, there are two terms: the photometry, also the radiometry. Photometry is basically discuss about to quantify the perception of the light energy. Perception of the light energy also very important. But in this class, we will mainly talk about the radiometry, which measure the light energy itself. It's one of the critical components for the photorealistic rendering. Basically, to generate photorealistic render, we need to measure the light energy. And then light energy flows through the space and varies with time, position, and direction. So we need to measure light along these factors. And basically the radiometric quantity is nothing but density of the energy at a particular places in time, space, and direction. In this lecture material, I will talk about the main radiometric quantity, and talking about everything is actually it may be very boring. So I will talk about main idea, and then if you want to know more about this radiometric quantity, I recommend you to look for my book. Now I'd like to talk about some of hemispherical coordinates. A lot of cases we need to use the hemisphere to define some of the radiometric quantity. So here we are showing that this hemisphere just two-dimensional surfaces, right? And then we just need to use the two parameters, theta and pi. And theta and pi basically correspond to this longitude and latitude. And then direction in the space can be defined by just define a point on this hemisphere. So here, if we just define a point here, then by drawing an arrow from the origin of the hemisphere that passing through the point, we can define this direction. And by definition of this theta and pi on the hemisphere, theta in the range of the 0 and pi over 2, and this pi actually they're defined in the 0 and 2 pi. Now I'd like to talk about solid angles. Some of you may not heard about the solid angle. So suppose that we had this. Let's start with this 2D example here. Suppose that we have this kind of 2D object here, and then we want to know that here actually also suppose that this actually the center this is kind of the center of this viewing, and then we want to know how much area these objects project to into this kind of this circle. Why we need to use this kind of cases? When you develop the random equation, we need to see that, so at some point we need to look at what are the possible surrounding environment here, as shown here. So basically we projected this all the surround. At some point we look at the ceiling, and as you can see we are seeing that this kind of light source and wall and other one. And at that point, this is actually by looking at this kind of surrounding view that are projected on the hemisphere, then we can see in what direction we can get what kind of energy we can receive. So in this case, actually, from the light source we can get a lot of energy. From other surrounding area, we get some not that much, but small amount of the energy. So that's why we need to have this kind of cases for developing random equation. So we need to use this kind of geometric configuration, which is actually known as the solid angle. So suppose that here we define this circle that has a radius of r, and then you want to know that this 2D object project onto some arc that has a length of the arc length L under the hemisphere. And then as you can see, if this is the light source, then as this projected line, which is L, as the L is getting bigger and bigger, we can see that we can get more energy and more energy from that light source. So that's why it's very important to measure the solid angle. Solid angle in this case actually defined by the L divided by R. So L is here again this arc length that are which is nothing but projected length on the hemisphere from that to the object. We can simply extend this 2D case into 3D case. So then this 3D object projects onto the certain area on this not 2D, this 3D sphere. And then in this case, solid angle defined by the area, the project area divided by r square. If we typically use the unit circle, unit sphere, in this case r become 1, then full circle actually corresponding to the 2 pi radians. So I didn't really talk about the unit for the solid angle. We use the radian for 2D. For 3D case, we use the step radians. But much more important is that the concept of solid angles. So now we defined so far we defined hemispherical coordinate. Now again I'd like to define the direction. This is the capital theta. So here actually this actual vector, and this direction can be defined by the specifying point under this unit sphere. So here actually here I showed this the area, but again if we define the point in this hemisphere, then we can define this direction from the center of the hemisphere that passes through the point. Then now I'd like to define a few these differential measures. First of all, I'd like to measure this differential area when you change this set time pi a little bit. Then how can you define this differential area here? So at that case, if the differential unit the delta of set time pi is very small, we can approximate that area as some sort of rectangular shape. Then I think I need to use this pen here. Then for this case, we can think about the width and height. Then if we change here actually this area actually located at the theta, but if we use if we change the delta theta here, if we actually here this width is delta theta, then the area, the dA, can be computed by d theta and r. Why? So basically we can apply the concept of solid angle, right? The solid angle, the basic solid angle can be defined by the arc length. In this case, we want to measure the arc length. Where's my point? The arc length and divided by the r here, right? And that's the solid angle, right? So in this case, this width corresponding to the basically this solid angle, this theta creating that arc length. Then given the equation, we can measure the arc length can be computed by the d theta multiplied by the r. Then how about this one, right? And then if the theta is actually the theta becomes 90 degree, then this region corresponding to the here, right? But if the theta becomes 0, then this arc length becomes getting very small, right? So then, as you can see, this height, I would say this is width. This width actually corresponding to as a function of some sort of theta function, right? To compute this width, I will move on to next slide. We can think about. I will change this. Pointer. We can think about it at that point. We can think about some sort of small circle that has a radius of radius starting from that point to there. Then how can you measure this length? Then here we assume that this is actually theta, right? This is theta, and then the length of the length from here to there is we denote as this x. Then by definition of sine theta, if we define sine theta computed by sine theta defined by this x divided by the r, right? Here this one x divided by r. Then we want to measure this x, right? Then x becomes r multiplied sine theta, right? Then once we know that this circle, then we can also apply the solid angle concept. So the corresponding to d phi, we can measure arc length corresponding to here, which I mentioned in the last slide. So that then we can simply compute by basically this is actually computed this is actually the radius at that circle. Then r sine theta and multiply the d pi. Then this is actually this is the width and height. Then we can compute this differential area. So if you want to know the more detailed derivation, I recommend you to look for my book. Then how can you measure this different solid angle? So here I define the different solid angle d omega. By definition of solid angle, this is divided by the dA divided by the r square. and then we can cancel all the r, so that actually it has a sine theta and d theta and d pi. We can compute the area of hemisphere, but we can also using this hemispherical this integration method. So we just measure this, we just integrate this solid angle over all the solid all the hemispherical space. Then by by utilizing the predefined the solid concept of the solid angle, then we can actually have this one d pi and sine theta and d theta, and we know that this the range of the pi and theta. Then I already forgot the calculus for the sine theta, but you can follow this equation. Then if we follow this one, if we to measure the area, we integrate the solid angle over the whole hemisphere. Then if we integrate all the solid angle, it becomes the area, and then this turns out to be the 2 pi. So far we talked about the hemispherical coordinate. Then we will actually utilizing those concepts for defining several the radiometric quantity. One of common radiometric quantity is irradiance. Irradiance is simply incident radiant power per unit area. So the power here I defined power P. So this is actually the this is the incident power per unit area. So visually, so at that point, how much energy we are receiving, So this is also known as area density of power. Its symbol is typically used by the E, but its unit is basically we typically use the power as a watt per meter square. So again, also the irradiance can be defined, can be known as this radiosity. If we consider this irradiance, area power density exiting, in this case actually here we talk about the energy in the receiving at that point, but we can also think about area exiting from that point. Area power density exiting a surface. This is called radiance exitance, or the typical radiosity. So that's why when we talked about radiosity equation, that's why it has a name of radiosity, since basically we measure the radiosity over there. So we didn't really care about in what direction, how much energy we are getting, but we just assume that this diffuse material, and then we just consider radiosity the incoming or the exceeding energy from all possible directions to the one point. The measuring irradiance or the radiosity can be visually like this. We put some sort of detector here, and then it detects at certain hole, and we can get energy all possible direction, and then at that time we can measure the certain energy known as the watt. And typically we can say it like this: a light source emitting 100 watts of the area watt with the area of the 0.0 meter square. That its radiant excitance, basically irradiance can be said that 1,000 watts per meter square. So anyway, irradiance radiosity is kind of pure independent energy that arriving at a particular point. Now let's talk about radiance. Radiance is another derivative measure from the power. Basically, here actually I skipped some of the also the low level concept like the power. If you look for my book, you can get a more detailed description on that concept. But here I will just skip that part since it's a little boring. I move on to irradiance and radiance. The radiance is the radiant power at direction x, but here in a particular direction theta. So typically I define the radiance in the form L. That's starting from x to that particular particular direction, this capital theta. This again this the vector consists of theta and pi, and then x is defined by the typically we define the radiance point in a 3D space. So this is actually 5D function, 3D for the position, 2D space for the direction. And this radiance defined by measured in the per unit area, also per unit solid angle. For defined direction, we use the solid angle. So this visual, the measuring the radiance can be visualized like this. basically we wanted to measure the energy at a particular point and particular direction. This is important quantity for the rendering. And this radiance, the radiance defined by this second derivative of power divided by the dA. Here also this is actually term I use this notation for orthogonal. The radiance defined on the orthogonal space. Here suppose that we are getting this energy at that particular direction here. Then on that slanted area here, the dA, but the radiance measured radiance defined under this orthogonal space here, so we can virtually think about it as kind of orthogonal space and dA orthogonal, and then per unit area, that orthogonal area to that direction, also this the unit solid angle here. So each unit watt divided by the meter square, also the unit of the solid angle. This irradiance per unit solid angle, again, is second derivative of the power. That's why I use the second derivative, and most commonly used term. And typically the radiance defined by this orthogonal space to that direction. But typically we receiving the radiance under this kind of non-orthogonal space in this dA, right? So we need to convert that. We need to project the energy in that are received under orthogonal to virtually define the orthogonal space to this arbitrary area dA. To do that, we typically introduce this cosine theta. So here is this is actually original radiance definition, and then we changed this dA orthogonal to dA, and dA multiplied by the cosine theta. Why we actually have cosine theta? Suppose that this is actually the angle of the theta here. Then this is actually this is the dA orthogonal, and then this is dA. Then suppose that we are getting the energy of the we are getting the certain energy here, dA orthogonal. Then this energy arriving into this the dA. As you can see that basically this energy, this same amount of energy actually projects onto more larger area, right? So energy will be reduced. Then how much? Actually turns out the cosine term. So this is theta. Then as you can see, this is theta. Then this is also theta, right? And then by definition, cosine theta is actually computed by dA over the dA orthogonal. Then you can derive the dA actually nothing but dA orthogonal. Sorry, the dA orthogonal actually the dA orthogonal by utilizing cosine theta term. Then dA orthogonal computed by the dA multiplied by this cosine theta. I didn't use I didn't derive the notation here. I just mentioned the term. If you just sit down and spend some time, you can very easily figure it out this one. Or you can refer to my book. You can see this detailed derivation over there. Why we talked about the radiance so far? Basically, the response of sensor, camera, human eye actually proportional to the radiance. So if we generate ray here, in the end, what we want to compute is the radiance. That's the radiometric quantity that we want to compute. Pixel value in image proportional to the radiance received from that direction. Also, there are many interesting properties. There are certain radiance actually moving from here to there in vacuum space, then the radiance energy is invariant along a straight line. But if there are some other material like the fog or some other one, then the energy will change, right? So at that cases, other than that cases, in the vacuum case, the radiance actually does not vary. If we have fog or some other materials, typically we say that participating media, that we need to develop more complicated approaches. But by now we just assume that the simple cases, basically in the space we don't have nothing in vacuum. Based on the invariance of radiance, we can also prove that suppose that we actually the emitting a certain radiance from x to the y direction, in the direction to the point y. So I used this note. I abused notice a little bit. So the radiance from x to the y can be proved to be equal to this radiance the received from y, received at the y from the x direction, from x to the y. So then we can actually define the radiance here and there. Then we can prove that they're actually equal to each other. Back then I used this question, this problem as a homework to prove this one. But basically, you can, if you're interested, you can refer to my book. There are based on the radiance, we can also derive this power and radiosity. Again, this definition of radiosity to measure the power. I didn't really define the power, but the power is nothing but we integrate this radiance over all the solid angle over all the area. That's the power. And then given this, so that's why actually we had this kind of integration. Based on the radiance value, but space may be space may not be the orthogonal to the theta, right? That's why we also had this cosine theta term that in the same region that I talked about before to define to convert this radiance value that are measured on the orthogonal area to the oblique space, and then the radiosity. Radiosity is nothing but given this radiance value adjusted by cosine theta over the solid angle, right? Radiosity actually defined on the particular point area, so that's why actually we just had this single integration. So that's why radiance is kind of a fundamental quantity, so that once we know that we can define the power and the radiosity. Okay, so far we talked about the physics of light and also the radiometry. Now I'd like to talk about material property. So far I talked about the diffuse and specular and glossy, but the diffuse material, also known as the Lambert material, is that once we receive the energy, it reflects the energy all possible directions in the same amount of energy. Either specular, it's like the mirror. If we receive this energy, we reflect the energy at the particular direction. Glossy is the kind of in between this ideal diffuse and ideal specular, so that if you receive this energy, it may emit the energy a lot at the case. If you look at this surface from there, you might see the highlight. But we don't reflect a lot of energy from here to there. So if you look at this material from there, then it may look dark. So we need to. So different material has this kind of reflecting this kind of the property. So to generate the realistic image, we need to consider this kind of materials. To support that kind of the glossy material, we typically use this BRDF function, bidirectional reflectance distribution function. So suppose that this is there's light, also we are receiving certain energy from that direction to that point. This x, also this direction is psi. And then in this material might reflect the energy from there to that direction, right? So this is actually the outgoing angle. This is the theta. So how can you measure this kind of BRDF function of the different materials? So we put there's certain source. There's certain light source, and then we actually capture the reflecting energy by with this camera, and by changing this by changing the position and direction of direction of this light source and camera, we can measure this function. Then how can define this BRDF function? The BRDF here defined by FR, whether the input is the x and the energy coming from this put side and outgoing angle theta, right? And this is actually this is defined by the radiance value that emitting from x to that direction. Here I used the notation of dl from x to the theta, and then incoming energy, the dE x that from this psi. Basically, this is the irradiance value and this is the radiance value, and then this is the radiance. Actually, we can measure with the camera, same thing. this irradiance value is that we treat that this light source has this certain very small source, so that we think about is the radiance value from here to there, also modulated by this cosine psi with this certain solid angle. And for the case of pure reimbursement, obviously this BRDF function is constant. Typically, this is actually computed by the rho d divided by the pi. We can starting from the definition of BRDF, further this pure reimbursement, we can prove that we can have this kind of one, but I will just skip that one. But this rho d is nothing but defined by the out of this energy input and how much energy we can reflect to there. So this is energy out, and then rho d typically in the range of 0 and d. And if the rho d is the one, it is actually reflecting all the energy. But there are many other distribution functions. We typically say BxDF. So one of the examples is BxDF, as here indicates scale, as in this case as referred to the scattering. The general form combining BRDF that I talked about before and BTDF. DT is actually transmittance. So this is actually here, and then if we receive the energy from here to there, and here also the hair strand also reflecting energy to there, so that it is BRDF. But here also this hair strand also the transparent. So it actually sum up the energy passing through the hair, and then also it also the exit from that direction. So that's why actually we need to think that passing through the hair strand also the BTDF. And also we can talk about the BSSRDF. This SS is a subsurface scattering. So if you look at the so far BRDF is that we receive energy from here to X direction, and then we assume that this material reflecting energy at that same location X. But if you look at the human skin, if you receive the certain energy and it actually passing through the energy here and there, and then it actually bounce here and there with the internal structure, and then it emit another location, let's say Y. So that we need to for this kind of material, we typically say this is actually subsurface. Sorry, not a surface, subsurface scattering. And so that actually this is a much more complicated function than BRDF. So far I talked about the physics of light, radiometry, material property. Now we are ready to move on to our final topic, random equation. The random equation, also known as this light transport, it actually describes steady state. We don't really care about how the energy actually how the energy propagate in time, but basically the energy moves so fast, so that we only care about this steady state radiance distribution in the scene. Our assumption is that we assume geometric optics and we achieve the steady state instantaneously. And then basically the random equation, it describes energy, light transport in the scene. Our input is that the light source, surface geometry, also this reflectance characteristic of surface, in other words BRDF. And output is the value of radiance at all surface points in all directions. Basically, given this input, we can compute the radiance value for the ray tracing cases. Let's look at detailed equation of the random equation. So suppose that we wanted to know what are the radiance value that starts from the x here, x, and then basically we are having the ray from x to the in the direction of L. So we'd like to know this radiance value that starts from the x in the direction of the theta. And then in the same manner, in the same manner that we derive for the radius equation, we consider two factors. One is the self-emitted term. So this surface may be this light source. At that cases, we might have the emitted light source, the L sub E that starts from the x to in the direction of the theta. plus with this reflected radiance. So we might we get this reflected radiance in the at the position of x to the in the direction of the theta. So basically, again this radiance value at here consists of two factors: self-emitted term and this reflected term. And if you look at the reflected the radiance here, L sub r in the direction of theta from x, then we need to think about the incoming incoming ray. So there could be any possible this incoming ray direction, and then we need to consider all possible incoming directions. So we need to integrate over this psi actually defined under this hemisphere. And then we need to think about it is the incoming radiance to the point of x from the direction of this psi, and then this surface may be reflected some of the incoming energy. So we need to consider this the BRDF here, and then this surface also this surface actually oblique to the outgoing direction. So that's why actually we need to consider this another cosine term, cosine theta at the position of x here, and then we integrate over all the possible solid angle over the hemisphere whose center at the location of x. So here actually I didn't really talk about this frequency wavelength, but this equation applicable all possible wavelengths. So overall, basically the derivation direction very similar to the radiosity equation. But the main difference is that in the random equation, we need to consider this the view dependent is incoming radiance, and then BRDF also that way we can also consider this the outgoing reflected radiance value. So let's look at let's talk about some sort of this visualization of this each term. So basically, we want to compute this reflected radiance value at the position of x to in a particular direction. Basically, we want to compute given a ray, we want to compute the radiance value for that ray, and then basically as we mentioned before, we need to go over all the incoming radiance of the hemisphere, right? Then basically this is nothing but at that point we just visualize, we actually visualize render this all the scene under the hemisphere. Basically I visualize this color information on the hemisphere into this rectangular shape. So basically this is the incoming radiance on the hemisphere, and then at that direction we might gather a lot of energy since it's light source, and at that case we might get less energy. And then for that location at that incoming direction, we consider the BRDF or cosine term, and then we integrate we integrate everything over all possible solid angle over this incoming the hemisphere. So now I'd like to talk about another formulation. So far I talked about the random equation in hemispherical coordinate, but there are another formulation known as the area formulation. Depending on what kind of paper you are reading for your paper presentation, some of paper use this hemispherical integration, but some other paper may use this area formulation. That's why I'd like to talk about these two different forms of the random equation. Essentially they are same, but they are just using the different coordinate. So here we just consider all possible solid angle, right? But there suppose actually before we talked about this incoming radiance to the x in the direction of psi, but basically we are just using the ray tracing, right? Ray tracing. So at that case we can also consider this position of y. That's actually a visible point. Visible point that are seen through from x in the direction of psi. So then we can reformulate this incoming radiance value, the L, at the radiance value to the x in the direction of psi. Then we can reformulate this radiance value like this. Basically, we can consider this radiance value that starts from the visual point x psi. Basically, we define this visual point y in that form. So basically, this is nothing but we want to know this is the same thing to the radiance value starting from the y in that direction. So this is kind of a little bit of the abuse of notation. I defined this direction as minus psi, like this. So they're actually essentially the same thing. Due to the menu, this invariance of radiance. Then we start from this random equation in the hemispherical form, and we define the y as visual point. We talked about this one, and then overall we want to actually we integrate everything over at the location of x. We integrate solid angle over the whole hemisphere, but we would like to integrate this random equation over all the visible point here under this surface. So we need to change this coordinate from the solid angle to this area formulation. But you might recall that we can apply the definition of solid angle. The solid angle is divided by the area divided by the solid angle is the area divided by r square, r square, and here basically this angle is also the dA. So we need to consider this cosine theta term, theta y. This is theta y is actually the angle at that position, since also this surface also oblique to the radiance value, and then we need to consider this radius value, which is nothing but distance from the x to the y. Then this is the prior defined the random equation in the hemispherical coordinate. We changed this integration of solid angle into any visible point on all surfaces over this differential area. So BRDF same thing, but we changed this incoming radiance from the L y minus L. The radiance value from the y to in the direction of minus psi. Y is actually visible point, and then we changed the solid angle into this area formulation, and basically the integration domain is the visible surface point. So then we actually introduced the sum of this visibility function as I will do that in the next slide. Here, so now basically this is the final random equation in the area formulation. I want to compute the radiance value from the x to the particular direction in the theta. So now also I consider the self-limited term, plus I integrate everything, all the point on the surface here. And then here, basically, the sum of point may be the visible from here to there, but sum of point may not be the invisible. So that's why actually I introduced this function v. V is the visibility function. This is invisible, so at that case, this visibility function turn out to be the 0. This is visible from here, so the actual visibility function is 1. So that's by introducing this visibility this function v, we can integrate everything over under the surfaces. And then this is cosine theta x, cosine theta y divided by this distance from x to this point, and this is this is actually distance, and then also this is BRDF, and this is the radiance value from y to in the direction of psi. So this is the random equation in the area formulation. In summary, we talked about two forms of the random equation. They're essentially the same thing. This is the hemisphere integrations. Reflect energy computed by integration over the solid angle with the incoming radiance and BRDF and cosine, one term of the cosine term over the solid angle. But also the area integration is actually we integrate everything over all the point in all the point on the triangle over the surfaces. This is the radiance value from y in the direction with the BRDF, and then there are two terms of the cosine theta x, cosine theta y divided by this r square. this is actually distance between x and y. Also, we need to consider the divisibility of each surface, each point in the A from the x. So that's why we introduced the divisibility function v. And then this is actually integrated over this differential area. By the way, I didn't talk about this one, this area formulation, but you might recall that when I talked about radiosity, I briefly talked about the form factor. I didn't really talk about the detailed equation of a form factor, but form factor is not, form factor over there is that how much energy we can see from the x to the y, right? That's the definition of form factor. But basically, area formulation is nothing but a form factor. Yeah. Back then, when you developed the radiosity, we didn't have the definition of the random equation in the area formulation, but later on, actually, we find out that the form factor is nothing but random equation in the area formulation. Okay, so far I talked about the different things. These are the actual. By now, I hope that you can understand the hemispherical coordinate and integration. Also, the various radiometric quantity. The most important one is the radiance. Also, I briefly talked about the BRDF, basic material function, and then I talked about how we can derive the random equation in the hemispherical coordinate. Also, I briefly talked about how we can convert it into another rendering equation in the area formulation. Okay, so next time I'll talk about multicolor random equation, which starts from this random equation, and then we will see how we can actually how can we solve this random equation. Again, the same thing, same homework, go over the next lecture slides before the class, and then watch 2 videos, go over 2 papers, and submit your summary before the every Monday class. Just 1 paragraph, English or Korean is okay.